What if the universe you see, the stars, the galaxies, everything you've ever known, is just a tiny, shimmering illusion? What if 85% of all matter is completely invisible, untouchable, a profound cosmic secret? Prepare to peer into the ultimate mystery, dark matter.
Imagine trying to solve a puzzle, but most of the pieces are missing. Or worse, they're there, but you can't see them. That's our universe. Everything we can see, every star, every planet, every atom in your body, makes up less than 15% of all matter. This invisible stuff, we call it dark matter, is the unseen cosmic glue holding galaxies together. By the end of this video, you're going to understand how we know it's there, what we think it might be, and why unraveling its secrets will redefine our place in the cosmos. Our first clue about dark matter came from looking at galaxies, specifically how they spin. Imagine a merry-go-round. The horses on the outside spin faster than those closer to the center, right? Well, that's what we'd expect for stars in a galaxy. The stars closer to the center should feel a stronger gravitational pull from the visible mass, orbiting quickly. Stars further out should orbit slower, just like planets further from the sun. But when we actually measured galaxies, we found something bizarre. Stars on the outskirts of galaxies were orbiting just as fast or even faster than the stars in the middle. It's like the horses on the edge of the merry-go-round were spinning at warp speed, defying all logic. The only way this makes sense is if there's a huge invisible halo of extra mass surrounding and permeating the galaxy, providing extra gravitational pull, a mass we can't see. If that wasn't convincing enough, dark matter plays another incredible trick. It bends light. You know how a thick glass lens can distort and magnify things? Well, incredibly massive objects in space, like giant galaxy clusters, can do the same thing with gravity. It's called gravitational lensing. They act like colossal cosmic funhouse mirrors. When we look through these galaxy clusters at even more distant objects, we see their light warped, stretched, and multiplied into bizarre arcs and rings. And here's the kicker. The amount of bending tells us exactly how much mass is in that cluster. Time and time again, the amount of light bending indicates far, far more mass than we can see with all our telescopes combined. It's like looking at a funhouse mirror that's much heavier than it looks, being held by ghostly, invisible hands. Dark matter isn't just messing with individual galaxies, it's the architect of the entire cosmic web. Think of it like the invisible scaffolding that built the universe. In the early universe, everything was hot, dense, and mostly uniform, but there were tiny, minuscule ripples in this cosmic soup, little bumps and dips in density. These are visible in the cosmic microwave background radiation, the faint afterglow of the Big Bang. These tiny ripples were the seeds. Gravity started pulling matter into these denser spots. But ordinary matter, the stuff we're made of, was too hot and energetic to clump together effectively in the early universe. It was constantly pushed apart by light. Dark matter, however, doesn't interact with light. It felt gravity's pull without resistance. So it started clumping together much earlier, forming vast, invisible gravitational wells. These wells then acted as giant gravitational magnets, pulling in ordinary matter, eventually forming the galaxies and galaxy clusters we see today. So we know dark matter is out there, but what isn't it? First, it's not just missing normal matter. We've looked for unlit planets, gas clouds, even tiny black holes. There simply isn't enough of that stuff to explain the effects we see. Plus, if it were normal matter, we'd detect some interaction with light or other forces. It's also not antimatter. Antimatter annihilates with normal matter, producing light. Dark matter does none of that. And it's definitely not just ordinary black holes. The dark in dark matter isn't because it's black or hidden behind something. It means it doesn't interact with light or any other electromagnetic force. It's fundamentally different from everything we've ever observed. Now, a quick but crucial clarification. Dark matter is not dark energy. This is a common point of confusion. Dark matter is matter. It has mass and it exerts a gravitational pull. It clumps together, helping to form galaxies. It pulls things together. Dark energy, on the other hand, is a mysterious force that causes the universe's expansion to accelerate. It's pushing things apart. They are two distinct, profound cosmic mysteries, both dark because we don't understand them, but they play opposite roles in the universe. Here's a truly mind-bending thought. Dark matter is passing through you right now. Billions of these particles are zipping through your body, through the Earth, through everything constantly, without any interaction, like ghosts or a cosmic wind you can't feel. This is because dark matter interacts only very, very weakly with ordinary matter, primarily through gravity. This explains why it's so incredibly hard to detect. It's everywhere, but it's almost perfectly aloof, a silent, invisible passenger in our cosmic journey. So, if it's not normal matter, not antimatter, and it's passing right through us, what is dark matter? This is the million-dollar question that physicists around the world are trying to answer. We know it's non-baryonic, meaning it's not made of protons and neutrons like everything we know. It's an entirely new type of particle, not part of our standard model of particle physics. The leading candidates are exotic particles like WIMPs, weakly interacting massive particles. As their name suggests, they're massive, but they rarely interact with anything. Think of them as tiny, super heavy, super shy particles. Another candidate is the axion, a much lighter particle, but equally elusive. Finding even one of these particles would revolutionize physics, requiring a completely new chapter in our understanding of matter. How do you catch something that barely interacts with anything? It's like trying to catch a ghost with a butterfly net. But scientists are incredibly ingenious. We've built massive underground laboratories, shielded from all other cosmic radiation, hoping to detect the incredibly rare collision of a dark matter particle with an atomic nucleus in a detector. It would be like a tiny, invisible billiard ball hitting another. Experiments at particle accelerators, like the Large Hadron Collider, are also trying to create dark matter particles by smashing other particles together at incredible energies. If they create them, the dark matter particles would simply vanish, carrying away energy, leaving a telltale imbalance. So far, no direct detection has been confirmed, but every failed experiment helps narrow down the possibilities, pushing us closer to uncovering this ultimate cosmic secret. Why should we care about this invisible, untouchable stuff? Because understanding dark matter isn't just about filling a gap in our cosmic inventory. It's crucial for understanding the entire universe. It dictates how galaxies form, how they evolve, and ultimately it influences the fate of the cosmos itself. If we discover what dark matter truly is, it will rewrite our textbooks, leading to entirely new theories of physics beyond the standard model. It might reveal new forces, new dimensions, new fundamental particles we can't even imagine. It's a quest to understand the very fabric of reality, a journey into the deepest, darkest corners of existence that promises to illuminate everything. So the next time you look up at the night sky, remember, the vast majority of what's out there isn't shimmering light, but an invisible, silent presence. A cosmic enigma that holds the universe together, waiting for us to finally pull back the veil and reveal its true nature. The greatest mysteries are often hidden in plain sight, or rather in plain unsight.